Welcome to Chapter 4 on directed graphs. Let V denote a finite set, and let E be a relation over the Cartesian product of V with itself. The pair V, E is called a directed graph and is denoted by G equals the pair V, E. The elements of V are called vertices or nodes, and the elements of E are called arcs or directed edges. In the diagram below, we have a depiction of a directed graph. The vertices are denoted by black circles, V0, V1, V2, V3, V4, V5, V6, V7. The arcs, or the directed edges, are denoted by arrows, segments with arrows. E0 is the pair V0, V1. The arrow points to the second element of the pair. E1 is the pair V1, V1. This is a very strange pair in which both endpoints of the arc are the same. They are V1, V1. E2 is the pair V1, V2. E3 is the pair V2, V3. E4 is the pair V3, V4. The difference between the pair E3 and the pair E4 is that in the edge E3, the first vertex is V2 and the second vertex is V3, whereas in the edge E4, the first vertex is V3 and the second vertex is V2. So I hope that now you understand what a directed graph is. I want to emphasize the arcs or the directed edges are pairs, ordered pairs of vertices. Good. Here you have a zoom of the previous graph, and I want to repeat again that we may have an arc that both endpoints of which are the same vertex, V1. Such an arc is called often a self-loop. Let's define paths or walks in a directed graph. So what is a path or a walk of length L in a directed graph? It's simply a sequence of the following form. You have a vertex, V0. This is the first vertex in the path. And then the next vertex in the path is V1, and V0, V1 is the directed edge E0. Then after V1, we have an edge E1, which connects V1 to V2, and so on. You can see a simpler depiction of this in the bottom of the slide. You see here, the path starts with V0. The first edge of the path, E0, connects it to V1. The second edge in the path connects it to V2, and so on and so forth until we reach V3. So formally speaking, this sequence, V0, E0, V1, E1, and so on, in this sequence, the vertices, the VIs are vertices. They have to belong to the set V. The EIs are edges. They have to belong to the set E. And each EI connects the vertex before it with the vertex after it. So E0 connects V0 to V1, E1 connects V1 to V2, and so on. Now, when we talk about a length of a path, we refer to the number of edges along the path. So in this path, we start with E0 and end with EL minus 1. So the number of edges in this path is L. Notice that the number of vertices in this sequence is L plus 1. Okay? Now let's make a few definitions. A path is closed if the first and last vertices are the same. A path is open if the first and last vertices are not the same or distinct. So notice that every path is either closed or open. It has to be one of the two. An open path is simple if every vertex in the path appears only once in the path. So we do not have repetitions of vertices in the sequence. A closed path is simple if every interior vertex appears only once in the path. A vertex is an interior vertex of the path if it's not the first or the last vertex. A self-loop is a closed path of length 1, namely it is a path that starts in V, there's one edge that connects V to itself. To simplify terminology, we often refer to a closed path as a cycle and to a simple closed path as a simple cycle. Let's see a few examples of such paths. Here we'll get to the part that we need. Let's look at these examples. The first example is of a closed path. We start with V0, we go to V1, to V2, to V3, to V4, to V5, to V6, which equals V3. We continue to V7, we return to V8, which equals V0. The first and the last vertex in the path are the same, and therefore this path is closed. Let's look at the second example. In the second example, we have an open path. Our open path begins with V0, continues to V1, goes to V2, continues to V3, V4, which equals V1, so it visits the same node twice, and then it goes to V5. Since V0 and V5 are different nodes, this path is open. In this example, we start with V0, we go to V1, V2, V3, V4, V5, V6. All the nodes along this path are distinct, and therefore this is a simple path. Let's look at this example of a simple cycle. We start with V0, we go to V1, V2, V3, V4, V5, and we return to V0. Here, this should be V6. Very good. Self-loop. Here we have a vertex with an edge, both endpoints of which are the same. Let's look at this funny example of a directed graph. This is a directed graph, which is a directed path, which is open and not simple. Good. We start with V0, we go to V1, continue to V2, V3, V3 equals V0, so this is the second time we're visiting the same node. Continue to V4, which equals V1. This is the second time we visit this node. We go to V5, which equals V2. We go here to V6. V6 is the same node as V0 and V3. In fact, we could go in this cycle forever if we wanted to, but after 2 rounds, we decide to go to V7. Okay, so our path goes V0, V1, V2, V3, V4, V5, V6, V7. Notice the first vertex and the last vertex in the path are different. Therefore, this is an open path. This path is not simple because the same node appears many times along the path. For example, this node appears as the first node V0, as node V3, and as node V6. This node also appears twice, and this node also appears twice along the path. Therefore, the path is not simple. Let's define a special type of directed graph, which is called a directed acyclic graph. Acyclic means that it doesn't have any cycles. So a graph is called a directed acyclic graph, or a DAG in short, if it does not contain any cycles. Okay? Let's look at an example of a DAG. Here we have a depiction of a directed acyclic graph with 1, 2, 3, 4, 5, 6, 7, 8 nodes. Now, how do we know that this graph does not have any cycle? Maybe there is a path that goes, I don't know, somewhere here and then maybe goes backwards or whatnot. Well, this is an acyclic graph. This graph does not have any cycles because there are no edges here that go to the left. Every edge goes either to the right or up. So if there were a cycle, we would start somewhere, go to the right, and in order to close the cycle, we would have to go to the left. But no edge, no directed edge takes us to the left. And therefore, this graph is indeed acyclic. And it is a directed acyclic graph. Consider the following suggestion that you may or may come up with. Let's make all the streets in our city one way so that the resulting directed graph is acyclic. Okay, so we think of the streets as directed edges in a directed graph. And we want the resulting directed graph to be acyclic. Would this be a good idea? So, for example, suppose you're looking for parking near your house. If the graph is acyclic, you cannot go around the block looking for parking. So that seems to be a good idea. But maybe it's not such a great idea, because in the morning, you leave your home and you drive to work, and then at the end of the workday, you want to drive back home. But if you find a way back home, that means that you found a cycle in the graph that takes you from home to work and back. And that's impossible if the graph is a directed acyclic graph. So, if the mayor were to make all streets one way, so that the resulting directed graph is acyclic, we might be able to get to work, but then we won't be able to get back. So that would not be such a great idea, would it? Okay, a few more terms. Consider an arc UV, a directed edge from U to V. We say that this edge enters V and emanates from or exits U. Okay? Now we can define the in-degree and the out-degree of vertices. The in-degree of a vertex V is the number of edges, the number of directed edges that enter V. The out-degree of V is the number of directed edges that emanate from V. Now, if a vertex has an in-degree which equals 0, we call it a source, because this is where things, are coming from. If a vertex has an out-degree of 0, we call it a sink, because you can't get out of it. Why do we need these terminologies? Because in digital circuits, sources correspond to the inputs and sinks correspond to the outputs. We'll talk about that later. Let's consider the following example. This is a depiction of a directed graph, the vertices of which are V0, V1, V2, up to V10. Is this a directed acyclic graph? The answer is yes. How do we know that for sure? Because I chose to draw this directed acyclic graph so that all the edges go to the right. And recall, if all the edges go to the right, you cannot close a cycle, because if you wanted to close a cycle, you'd have to go back to the left. Okay, consider V0 and V6. How many paths do we have from V0 to V6? Well, the first path is V0. Along E0 we go to V2. Along E3 we go to V4. Along E6 we go to V6. The second option would be to leave V0 through E1, reach V1, continue along E2, reach V3, continue along E4, and reach V6. So we have two different paths that connect V0 to V6. What is the integree of V5? Here's V5. We see that there are four edges which are incident to V. V5 participates in four edges, two of which enter V5, this is E5 and E8, and two of which emanate from E5, this is E11 and E9. So the integree of V5 is 2 because of the edges E5 and E8. And the outdegree of V5 is also 2, but because of the edges E9 and E11. What about V4? What can we say about the outdegree of V4? Well, we have three edges which are incident to V4, E3, E5, and E6. E3 enters V4, E5 emanates from V4, and E6 also emanates from V4. So the outdegree of V4 is 2. Okay, let's look at this directed graph and ask ourselves, does this graph have a vertex which is a source? So, for example, V3, is it a source? It's not a source because there is an edge which enters V3. This is E2. So, do we have a vertex here that has 0 edges entering it? Yes, V0. V0 has 3 edges which are incident to it, but all of them emanate from V0. And there are 0 edges which enter V0. Therefore, V0 is a source. What about sinks? Do we have sinks in this graph? We're looking for vertices that no edge emanates from them. For example, if I look at V6, I see that there is an edge which emanates from V6. This would be E10. So V6 is not a sink. Okay, let's look for a sink. Oh, there are 2 sinks in this graph, V9 and V10. V9 has 2 edges emanating, 2 edges incident to it. Both of them are enter V9. E13 enters V9, E9 enters V9, but no edge emanates from V9, therefore V9 is a sink. What about V10? Same thing. We have 2 edges which are incident to V10. They enter V10. 0 edges emanate from V10. Therefore, V10 is a sink. Okay. Finally, having made all these definitions, we are ready to make a few lemmas. These are lemmas that describe properties of directed acyclic graphs. The first lemma. Suppose I have a non-simple path in a directed graph. Then this path must contain a simple cycle. Okay, let's prove this lemma. Okay, so assume that P is not a simple path. We want to prove that there exists a subpath of P. This is a subsequence of the sequence P, such that Q is a simple cycle. How do we prove this lemma? Well, P is a sequence of vertices. Let's denote them by V0 up to VL. Now, let's look for a pair ij. These are indices, I and j. This pair is the closest pair of repeating vertices in the path P. Namely, I is less than j, vi equals vj, and if you have another repetition of the form vl equals vk for l less than k, then the difference j minus I is less than or equal to k minus l. This means that this pair vi, vj are the closest, in some sense, pair in which you have a repetition. Now, having taken this pair, which is the closest pair of repeating vertices along the path, we notice that Vi up to Vji minus 1 are distinct vertices. Because if I had repetitions in this subsequence, then this repetition would give us a smaller difference than the difference we have between j and I, and that would contradict the second condition for the choice of I and j. So all these vertices are distinct, and therefore the path that starts in Vi goes to Vi plus 1 and so on until we reach Vj is a simple cycle because we do not have repetitions in the interior nodes of the subpath. The second lemma we want to prove is that if we have a DAG over n vertices, so n here denotes the number of vertices or the cardinality of V. We want to prove that the length of every path in G is at most n minus 1. You cannot have long paths in a DAG. Okay, the paths are bounded by n minus 1. How do we prove this lemma? Okay. So again, let G denote a DAG. We want to prove that every path in G has length at most n minus 1. Okay, I remind you that the length of the path is the number of edges along it. Okay. First of all, notice that every path in G is simple. And the reason is because if P is not simple, then by the previous lemma, there exists a subpath of P which is a cycle, and that would contradict the fact that G is acyclic. Okay. Let L denote the length of the path. And let Vi, I goes from 0 to L, denote the sequence of vertices in P. Then, all these vertices have to be distinct. Therefore, by the pigeonhole principle, L plus 1, the number of vertices in this sequence, cannot be greater than n. And therefore, L is less than or equal to n minus 1, which is what we wanted to prove. The third lemma says that every DAG has at least one sink. Let's try to prove that. Namely, the fact that we were able to find the sink in this, the fact that we were able to find the sink V0 in this DAG is not a coincidence. The claim is that we always have a sink in a DAG. Okay, how do we prove this? So, consider a DAG G. We want to prove that there exists a sink V in the DAG. Assume, for the sake of contradiction, that every vertex in V is not a sink. What would this imply? It would imply that every path P can be extended by an edge. Look here. This is a path in black. This is P. It ends in V. Now, V is not a sink by our assumption. Therefore, there exists at least one edge which emanates from V. Let's say it goes to U. That means that we can add this green edge to the end of P to make it longer. This means that, in fact, G contains a path P of length V, where V equals the cardinality of V, right? Now, the cardinality of V in the previous lemma was n, and in the previous lemma we said there could not be a path of length n. Every path has length at most n minus 1. So we get a contradiction to the previous lemma, and that completes the proof. Finally, we want to prove that every DAG has at least one source. If we look at the DAG we had before, this means that the fact that we were able to find the source in this graph, in fact, we were able to find, I confused the source with a sink. Every DAG has at least one source. Let's go back. So, previously I should have said that every DAG has a sink, and we were able to find it, in fact, two sinks, and now we're referring to the source. I apologize. So now we want to prove this corollary. How do we prove it? Good. So one way to prove the claim that every DAG has a source is to use a path extension argument as we used before. The idea would be, instead of extending the path at the end, we would extend the path in the beginning. Okay? But let's try to use a different proof, which will also introduce a new definition. Let's define the reverse of G. What is the reverse of G? So G is a directed graph with a set of vertices V and a set of edges E. The reverse of G is a directed graph over the same set of vertices, but a new set of edges denoted by the reverse of E. What is the reverse of E? Well, we say that X, there is an arc from X to Y in E, if and only if there is an arc from Y to X in the reverse of E. So reverse of E is simply taking all the edges of E and reversing their direction. If they went from X to Y, now they go from Y to X. Now, notice that if G is a DAG, if G is a directed acyclic graph, then the reverse of G is also a directed acyclic graph and vice versa. Right? Why is this true? Well, suppose that the reverse of G is not a DAG, namely, it contains a cycle. Now walk along this cycle in the reverse direction. You get a cycle in G, which is a contradiction because G is acyclic. Okay, and you could also prove the converse direction using the same argument, walking around the cycle in the reverse direction. Now, if a vertex V is a source in G, then it is a sink in the reverse of G, because every edge that, if V is not a sink in the reverse, that means that there is an edge that emanates from V. The reverse of that edge enters V, which means V is not a source. So we get that if V is a source, then V is a sink, and we can prove the converse direction using a similar argument. Now, by the previous lemma, the reverse of G, being a DAG, has a sink. But this sink is a source in G, and that completes the proof. Okay, so now what we want to do is we want to see how we can list the vertices, how we can specify an ordering over the vertices of a directed graph. And this is done by introducing a bijection. Bijection, I will remind you, this is a one-to-one and onto function from V, the set of vertices, to the set 0, 1, 2, 3, up to n minus 1, where n denotes the number of vertices in V. Now, why does this define an order? Because we can think of Vi as the vertex for which pi of V equals I. And now we can write the vertices V0, V1, V2, V3, up to Vn minus 1. So this bijection pi specifies an ordering over V. Now, every vertex appears exactly 1 in this n tuple, V0 up to Vn minus 1, and such a tuple is often called a permutation of the vertices. And we are interested in permutation of the vertices that satisfy a special condition. Okay, so what is this special condition called? It's called a topological ordering. And the idea is, order the vertices of G so that if U precedes V, then V, U is not an arc in the directed graph. Okay, so let me show you a depiction of what this means. Look at this drawing. What do we have here? We have here a directed acyclic graph with the vertices V0, V1, V2, V3, V4. And we have the edges in black from V0 to V1, from V1 to V4, and so on. Now, all the edges in this drawing are go to the right, and I do not allow any edge to go to the left. Okay? We call this a topological ordering of the DAG. This is the first vertex, this is the second, third, fourth, fifth. All the edges go to the right. This means that if I is less than or equal to j, then there's no edge from Vj to Vi. Now notice that the special case I equals j is actually covered by the fact that we're dealing with a DAG. So we never have an edge from Vi to itself. We do not have self loops. But if I is strictly less than j, we do not allow an edge to go to the right from Vj to Vi. Now the contrapositive of this statement, let's see, the negation of I less than or equal to j is I is greater than j. The negation of Vj Vi is not an arc is Vj Vi is an arc. So the contrapositive of the first line is if Vj Vi is an arc, then j is less than I. Okay, so when we look at a topological ordering, we do not allow the arcs to point to the left, and the main application of topological ordering is for simulation of digital circuits. We will get to that later. Okay, so now I want to define what a topological ordering is. Let G be equal to the pair V, E, and let G denote a graph with n vertices. A bijection from V to the set 0, 1, 2, 3 up to n minus 1 is a topological ordering of the vertices of the directed graph if whenever uv is an arc, then pi of u is less than pi of v. Okay? And we already saw that by contraposition, this means that if pi of v is less than or equal to pi of u, then u comma v is not a directed edge. So we have a new definition. Now, let me try to explain how a directed acyclic graph can be used in order to specify a procedure that consists of many subtasks. I'll use a different example than the one used in this slide. Let's go here. Okay. So let's use a DAG in order to model the steps that you need to do in order to perform some task. Okay? So what we have here is the task of preparing an omelette. This is your opportunity to learn how to prepare an omelette. And if you already know how to prepare an omelette, this is your opportunity to verify that I know how to prepare an omelette. Okay, so what I wrote here are subtasks that are required in order to prepare an omelette. Heating the pan, oiling the pan, pouring the egg into the pan, removing the omelette, and of course turning the heat off. Now, there are directed edges between these subtasks of preparing an omelette, right? What do these directed edges signify? Well, what they signify is precedence. So if I have a directed edge between heating the pan and pouring the egg into the pan, this means that I need to heat the pan before I pour the egg in the pan. Okay? So, suppose that a single person now wants to prepare an omelette. So a single person can do only one subtask at a time. How should this person order these subtasks in order to prepare the omelette? Well, what that person needs to do is order the subtasks in topological ordering. This is all that you need to do. So notice, this ordering is good if you oil the pan before you're pouring the egg, because we have a directed arc from oiling the pan to pouring the egg into the pan. It's also good if you heat the pan before or after you break the egg. Okay, so these two subtasks do not have any precedence between them. You can either first heat the pan and then break the egg, or you break the egg first and then you heat the pan. Notice when I'm breaking the egg, I'm not breaking it into the pan. I'm breaking it into a dish on the side. I'm scrambling it, and then I pour it into the pan. Okay, this is important. Now, a bad thing to do would be pouring the egg into the pan before oiling the pan, right? So you first have to oil the pan, and then you have to pour the egg in the pan. Okay, now, let's look at this precedence graph of this DAG, which describes how to prepare an omelet. And you could ask yourself the question, if I'm a single person and each subtask here takes, let's say, 3 minutes, this means that the amount of time it would take me to prepare an omelet is 3 minutes times the number of tasks. So the number of tasks here is 7. It would take me 21 minutes to prepare the omelet. This is not a very nice thing. It should take 3 minutes, but for the example, let's say it takes 21 minutes. Okay, now, suppose two friends want to prepare an omelet together. Can they do it faster? Well, seemingly they could, because the first person could heat the pan, and while the first person is heating the pan, the second person could break the egg, right? So we would save, let's say, a time unit or 3 minutes, as we said before, because we wouldn't need to heat the pan and then break the egg. We could do this in parallel. Another question you could ask, well, what happens if 3 friends want to prepare the omelet together? Could they speed up the time it takes to prepare the omelet? And it seems that they could do that, because person 1 would heat the pan, in the same time person 2 would break the egg, and in the same time person 3 would oil the pan. This would of course require some coordination between these two subtasks, because while oiling the pan you're heating it, but let's assume that these 2 friends are coordinated and they can do this task together. So all these 3 tasks would be done simultaneously. Then we would have a single task of scrambling the egg, which we would have to do, and then we would do this task, this task, this task. So in fact, only in the, so to speak, first time unit, the 3 friends are busy. After that, only 1 friend is working, and the others are sitting idle. Okay? So what this issue raises is the issue of parallelism. Does the fact that I have more people that can help in performing the task, does that help speed up the time it takes to complete the task? Good. I want to now describe an algorithm that, given a directed acyclic graph, computes a topological ordering of the vertices of the DAG. Okay? We call this algorithm TS for topological sorting. The input is a directed acyclic graph G, and the output is a topological ordering of G. Now I will use the following notation in the description of the algorithm. E sub V, this is lowercase v, is the set of all arcs such that E either enters V or emanates from V. Sometimes we call that E is incident to V. Good. How does the algorithm go? This is a very simple algorithm, but it is a recursive algorithm. So being recursive, it consists of 2 parts: the base case, when the number of vertices is 1, and the reduction rule, when the number of vertices is greater than 1. Okay, so the base case is trivial. If the number of vertices is 1, there's only 1 vertex. Denote this vertex by lowercase v, and all you have to do is assign a number to v. Pi of v equals 0. Clearly, this is a good topological ordering of a graph that consists of a single vertex. Now, here comes the reduction rule. The reduction rule, if you have more than 1 vertex, is you find the sink in the DAG. Now, we know that every DAG has a sink, so we can find such a sink. We simply scan all the vertices one by one and look for a node whose out degree is 0. And we're guaranteed to have one because we have a lemma that tells you if the graph is a directed acyclic graph, then it has a sink. Okay, so V is a sink in the graph. Now what do? We take V and we remove it from this set of vertices, and we remove from the set of directed edges all the edges which are incident to V. Now we have a new DAG with one vertex less, and we apply the algorithm recursively to this smaller DAG. So this invocation of TS on the smaller graph gives us a topological ordering of all the vertices except for lowercase v. So now what we do is we extend pi by setting pi of v to be the number of vertices minus 1. Okay, let's give an example of an execution of this algorithm. In this example, our graph consists of 4 vertices, u, v, w, z, and it has 4 edges. The edge from u to v, from v to z, from u to w, and from w to z. 4 vertices. Okay. Now we invoke the algorithm TS on this graph. The stopping condition does not hold because this graph has 4 vertices, so we apply the reduction rule. The reduction rule looks for a sink. The sink in this directed acyclic graph is z. Good. We might have multiple sinks, but here we have only one. We assign pi of z to be 3. Why 3? Because we have 4 nodes, so pi of z is 4 minus 1. This is 3. Now we want to apply the algorithm recursively. On what? On the graph obtained by deleting z and all the edges which enter z. We're left now with 3 nodes and 2 edges. We apply the algorithm recursively to the remaining graph. Now we have 2 sinks. We can choose either one of them. We chose v, and we give v an index. Pi of v equals 2. Why 2? Because we have here 3 nodes. We subtract 1, we get 2. Okay, very good. Having chosen the sink, we erase it and all the edges which enter the sink v, and we're left now with 2 vertices. We're left now with 2 vertices, u and w. Good. Now we invoke the algorithm recursively on this remaining graph. This remaining graph has a sink, w. We assign pi of w to be 1 because it has 2 vertices, so 2 minus 1 is 1. And we erase w and the edge entering w. We're left with a graph that consists of a single node. A graph with a single node, the stopping condition applies to it. Namely, all we need to do is assign pi of u equals 0. So what the algorithm does is it takes this DAG and it assigns pi of z equals 3, pi of v equals 2, pi of w equals 1, pi of u equals 0. Notice that all the edges go to the right, go from a low index to a high index. For example, the edge from v to z goes from index 2 to index 3. Now, I hope you understood by now what algorithm TS does. We want to prove that it is correct. Namely, if we input a DAG, then the output of the algorithm is a valid topological ordering of the vertices of the DAG. Let's prove this claim. So we want to prove that if G is a DAG, then pi is a topological ordering. The output of the algorithm is a topological ordering. The proof, the algorithm is a recursive algorithm. So the proof will proceed by induction on the number of vertices. The induction basis for the case that the number of vertices equals 1 is very easy, because we take the single node in V and we assign pi of V equals 0, and clearly this is a valid topological ordering because there are no edges in the graph. Okay. The induction hypothesis says that what we need to prove, this star, holds if the number of vertices equals n. Now we want to prove the induction step, namely we want to prove that the claim denoted by star holds for graphs that contain n plus 1 vertices. Good. So now let's see. What does the algorithm do? The algorithm picks a sink, V, the existence of which is guaranteed because we know that every DAG contains a sink. Now, the induction hypothesis tells us that the output for the remaining graph without V and without the edges which are incident to V is a valid topological ordering of the remaining vertices. Now, the number of remaining vertices is n because we started with n plus 1 vertices and we omitted one vertex. So we're left with n vertices. And we assign them numbers from 0 to n minus 1. And then what we do is we take this sink and we assign it pi of V equals n. So what do we have here in this diagram? We have the vertex V, this is the sink, it's given pi of V equals n. We have the remaining vertices, which are given numbers between 0 and n minus 1 by the recursive call to the topological sorting algorithm. Now we want to claim that pi is a valid topological ordering. So consider any directed edge from x to y in E. We have three cases. Either both endpoints are over here. But if both endpoints are over here, then pi of x is less than pi of y because pi is a valid topological ordering of this part because of the induction hypothesis. So the first case is easy. Second case is that x equals v, so x is here. But if x is here, then that means that we have an edge that emanates from x, and emanates from v. And that would contradict the assumption that v is a sink. So this case could not hold. Okay, finally, we're left with a case that y equals v. Well, if y equals v, then all we need to show that pi of x is less than pi of v. But this clearly holds because pi of v is n, and pi of x is in the range 0 to n minus 1. This completes the proof. Before I finish, I want to raise a question. The algorithm for topological sorting is designed to sort the vertices of a directed acyclic graph and compute a topological ordering of the vertices. What happens if we input a directed graph that is not acyclic, namely contains a cycle? What would the algorithm do? If the algorithm succeeds in computing a topological ordering, then that would mean that the graph is acyclic, because once you have a topological ordering, you're guaranteed that all the edges go to the right, so to speak, which means that there are no cycles. So, if we start with a directed graph that contains a cycle, we cannot hope to compute a topological ordering of it. So what would this algorithm do? So my question is, suppose that you input a graph which is a directed graph but contains a cycle, and you execute this algorithm on this cyclic graph. What would the algorithm do? Thank you very much.